Hi, Amy. How are you doing?
I'm good, thank you. How are you?
Good, good. So, how do you find calculus?
Um, Not that bad. It's actually, it's all making sense now.
Mhm.
Sketching, graphs, like I actually get it now, and I think it's stuck here. Yeah,
Very
so
good.
it's good.
Did you try some question papers from your book, examination style questions?
Not yet.
Got it. It's
I
time.
know. Sorry.
Okay. So,
Yeah,
anyway, today I'll give you some practice with similar kind of questions, and I hope that is going to help you. So,
yeah.
you're actually ready to take up a test on calculus, right? So, you should make an attempt now uh,
Okay.
to look into the type of questions they're going to ask you in the examination. Okay. So let me share with you the screen and then we'll talk about some questions which could be asked in examination. Okay. So here is a very important test paper which I want to share with you. What I've done here is that taken three questions, and these three questions will actually remind you of three different concepts. So we'll touch base on, see, calculus. We come to calculus when we have learned most of the mathematics, which you are required to know at school level, correct?
Hmm.
And you have to apply all the principles which you have learned so far when you are attempting a test paper in calculus. To give you just a gist of it, I've just taken three questions for you. I'm calling this as applications, find equation, and analyze stationary points. Do you remember what are stationary points?
Yeah.
Yeah, what are
So
they?
when the derivative equals zero,
Perfect. And how when you analyze, what do you figure out?
the local maximum or minimum.
Perfect. So based on that, we have three questions. Question number one. Consider a right triangle with hypotenuse 4 centimeter. Okay. We have three parts to this. Show that the area of the triangle is a equals to half of x times square root of 4 square minus x square. Prove that the maximum area of this triangle is 4. Write a general expression for the maximum area in this situation. Okay? So in the question itself, we are kind of guiding you as it is in most of the GCSE test papers. We guide you through the solution. So you need
Yeah.
to first find the expression for area and then find the derivative and analyze the derivative to find the maximum and then write a general expression that this is a particular case when we are giving you hypotenuse of 4 centimeters. It could be age. In that case, what is your result, right? I've purposely given you part three so that if this kind of a question is there in your test paper, uh, the value doesn't really matter. You should be working with the general expression of age, right? So that should help. Can you read question number two for me?
Yeah. Consider a cylinder of radius r with fixed capacity of 1000 centimeter cubed. A. Show that the surface area of the cylinder is A equals 2 pi r squared plus 2000 over r.
Correct.
B. Show that the rate of change of area with respect to the radius is 0 when r cubed equals 500 over pi.
Perfect. So that is a good question. You're given some value, which is the fixed capacity or the volume. If
Yeah.
that is the case, then you are also given two equations, and that is we are saying that surface area is 2 pi r square plus 2000 over r. Now, first question is, if I say that the capacity is V, okay, so if I say this is V, in
Yeah.
that case, what will change here? Tell me.
What will change?
Yeah. Instead of 2000, 2000 is because of 1000, correct? It will become 2 times V, correct? Twice the capacity.
Oh,
So you
yeah.
are given a value. So in your textbook, when you're looking into examples, try to see the general solutions, right? So that you're flexible. Now, it doesn't matter whether the capacity is 1,000 or 10,000, right? Method
Mm.
is up to you. But if you could understand how a general formula can be related, it is very good, especially for a multiple choice test paper, right?
Oh, okay.
Now, R cube is given to you as 500 over pi. 500 is half of 1,000. You see that?
Oh,
Half
yeah.
of that capacity divided by pi is R cube. So look at the question, try to get more than what it is.
All
So
right.
that ways you are going to, really learn while you're learning, right?
Yeah, that makes sense.
Got it? Read
Yeah.
question number 3 now.
Question 3. Consider a sector with area of 100 centimeters squared.
Mhm,
A. Find domain of the radius r of the sector.
mhm.
B. Relate perimeter P with radius. And C. Find the minimum value of P.
The perimeter, right? Okay, how will you do
Oh,
this?
um, okay, so because it says a sector with area 100 centimeters squared,
Yeah.
area of a sector, I mean, I learned that in GCSE. It was like theta over 360 times pi r squared.
Okay, right. So what you're saying is kind of correct. Remember, when we are working in calculus, all the units are in radians. Okay.
Oh,
So theta is in radians. So instead of 360, you'll use 2 pi. Okay. Now you're correct. So the whole circle has infinite symmetry. Okay. And area of the circle is pi r square. We just want to take a pi of it, one sector, which is shown here in green, right?
yeah.
So that will be ratio of the angle. So pi r square is the total times theta over 2 pi.
Oh, okay.
That becomes the formula for the area of sector. Is it? Take a note of this.
Yeah.
Pi r square times theta divided by 2 pi. So when you cancel pi and pi, you are left with what?
2 times 1,000 over
No,
r.
don't put 100. Don't put 100. Just general.
Oh.
Okay, yeah. So
Oh.
area of sector is pi r square times theta over 2 pi, correct? So pi and pi cancel. So you get a formula which is half r square theta.
Oh. Yeah, yeah.
Area, write down the formula for area, correct? Of course, when you solve the question, instead of A, you'll put 100 and then solve, correct?
Okay. Yeah.
Right. Do that later. But now you understand the formula and how to derive this particular formula. At times, you have to, Emmy, at times we have to connect with formulas which we had learned way back.
Mm.
If we understand how they were derived, we can recall them. Perfect.
Yeah.
That's a good exercise. Well, fortunately for you, many times in the test paper, they give you all the formulas also. So on the very first page, you might find all the formulas or somewhere in between, right?
Oh, okay.
So that could be a help, but it's always good to know them and how we derived.
Yeah.
So, I would actually like you to go through these questions, provide solutions, and then we can discuss the solutions after about half an hour.
Okay.
Does it sound good?
Yes. Yeah, sounds
I
good.
think half an hour should be a very good time to solve all these three questions. Okay?
Yeah. Okay.
So, see you after half an hour.
All right. Thanks, sir.
Thank you.
Hi, sir.
Hello, how are you doing?
I'm all right. How are you?
Good, good. So, how was the test paper? How did you find these three questions which you had been working on?
Question 2 and 3. They were all right. Question 1, I didn't really get B and C.
Oh, you didn't really get B and C? Okay. So, we'll
No.
discuss the solution for question one. And it's
Okay.
good that you got question two and three. That's great. So, uh, in question one, you got part A, right?
Yeah.
Okay. So, let me share with you the solution and then we'll discuss from there onwards. Okay. So what I did was that uh, basically, whenever you want to solve a question, it's a good idea to define variables and sketch a diagram. So we're talking about right angle triangle. We are given the hypotenuse in this case, which is 4 centimeters, and we are actually interested in maximum area of this particular right triangle. So we can say that the two sides are x and y. The hypotenuse is 4. They are related with Pythagorean theorem. So we get our equation, which is x square plus y square equals to 4 square. Y square is 4 square minus x square. Y equals to square root of 4 square minus x square. Now at
Yeah.
this stage, I mean, it's very important to also understand the boundary conditions, right? Within the radical sign, we cannot have anything negative. So clearly, uh, x should be less than 4. X and Y are lengths, so they should be greater than 0 also, correct? So we have
Yeah.
restriction on X, which is between 0 and 4.
So it's always good to write the
Yes,
restriction.
right.
Okay.
Now, here, let me deviate from the particular solution which I have here. We will be doing this chapter on finding absolute maximum and absolute minimum when the boundary condition is given to us. So to give you a heads up, which is a part of the solution can be used if you have learned that chapter earlier, that whenever we have a restricted domain, in that case, extrema can occur either at the critical number or at the endpoints. For
Oh, okay.
example, yeah, for example, if I have a straight line, correct? If for a straight line there is no critical number, correct?
Mm-hmm.
Because there's no turning point. It's,
Yeah.
but it does have a minimum and a maximum, which is absolute minimum and absolute maximum. Do you see that part?
Yeah.
It happens at the end point, correct?
All right. Yeah.
So we're talking about absolute maximum and minimum. And when we use the term large as possible, it really means absolute maximum and absolute minimum. So in our solution, we should test the value at the endpoints, which are 0 and 4 also. Is that clear?
Oh, okay.
In
Yeah.
this particular case, if I substitute 0, I get area 0. If I substitute 4, I again get area 0. Now, since both the values give me 0 area, whatever area I find will be maximum. Is that a good logic?
All right. Yeah.
So my critical number is going to give me a maximum, right?
That makes sense. Yeah.
Yeah. So that is a good logic sometimes. You may avoid interval table using this particular logic. That's the huge advantage. And it can save a
A
lot of,
lot of time.
you get my point now?
Yeah.
We'll, we can consider this example as part of our next chapter where we are looking into boundary conditions. And we are saying that we will get absolute value of maximum or minimum either at the boundaries or at the critical number. Is it
Mm.
okay?
Yeah.
So if the boundaries are giving you 0, then the critical number is giving you maximum. If everything is positive, of course, right?
Yeah.
Okay. Area is positive, so it is maximum. So you do not have to do this part. You get the idea?
Yeah.
How this we can answer. Now, since your exercise involves analyzing the first derivative, I have included this. Is that clear?
Yeah.
Okay. Now, first part you did, that is great. We found that the expression for area is half of x times square root of 4 square minus x square. Most of the time, we will not write 4 square, we write 16 minus x square, and that will be the formula given to you. However, I wanted you to see the equation as it moves forward like a general equation. That number 4 could be anything, right? Let's say h. So if it is that, number, which is a general equation, it will be half x h squared minus x squared. You get the idea, right?
Yeah.
We will maintain the value of 4 and think about 4 could be any number. It's just a variable, right? Think like that. And then we'll get to the result. Now, let's see what have I done on the derivative part. So the very first step is we need to find the derivative. Derivative is product rule, correct? X times square root of this. So derivative of x is 1. So we get the first part, which is half of this. You could actually take half outside as a common factor since it is a constant, right?
Mm.
You could take that and then that simplifies a bit. Now, derivative of the second part, which is square root part, right, will be half of that square root term comes in the denominator times inside function derivative. Inside function is minus x squared. Minus x squared derivative is minus 2x.
Yeah.
Correct? So once you get that, you can simplify it. Cancelling the terms, so that 2 and 2 you could cancel, correct? So once you do that, you do get half of this, and this minus makes this as negative, and you got half x times x is x squared divided by square root of 4 square minus x squared. Then you take the common denominator, right?
Mm.
Half is also common. We take this also as common. When you multiply these, cross multiply, the radical sign vanishes. You get x square minus 4 square minus x squared, left with minus x squared on this side. So you get 4 square minus 2x squared. Is that clear?
Yeah.
Okay.
Mm.
Now you could just, you could actually simplify this further. I have purposely written 8 minus x squared since I wanted to come out with a general formula. Okay.
I'm just a bit confused where I went wrong.
Okay.
So I got
Yeah.
so I was trying to find the derivative of the half x 4 squared minus x squared, but I put it to the half, and I think that's where I went all wrong. So I got half times, but then so let me just reverse
Yeah.
it. So let me go half times
Yes.
square root 16 minus x squared
Yes.
plus half times 16 minus x squared to the minus a half
Correct.
times minus 2x.
That is correct. That is what I've written.
Then I was trying to take out the half 16 minus x squared to the minus a half out.
Yeah.
Yes, so then I got x. I got, oh no.
Okay.
Wait, would it be 1? It would be 1 add minus 2. See, that's where I don't know, because I'm taking a factor outside and it's all getting a bit confusing.
At the end, what did you get?
I didn't get anything because it all got messed up. Maybe I'll just send it to you.
Right again, Amy,
Yeah.
right? So anyway, so when you actually solve it, you are quite right up to this stage. Maybe you have to take half as common factor, correct? And
Yeah.
the square root is common denominator, then it will be kind of not so difficult.
Okay.
So try to do it. We were in a rush. We just wanted to do everything in these 20 minutes. So that's okay. But let's understand this. So once you have this general form, you have a critical number, right? Denominator can be 0, numerator can be 0. That's why we are calling it a critical number. Now we need to analyze it. So endpoints in this particular case could be 0 and 4. We already found that the area is 0 for that, correct?
Yeah.
So we'll just focus on the value, square root of 8, which is giving numerator 0, right? X square equals to 8. So we have taken 2 points on left and right side of square root of 8. Sometimes you could write 2 square root 2 for square root of 8. But I'm keeping square root 8 only because I want to generalize the solution. Look at like, as it could be. Not resolved, simplified. Okay. So once you do that, you find that for 2, 8 minus 2 will be positive, right? 2 squared, virtually positive 4. And if the x value is 3, it'll be 9, 8 minus 9 will be negative, so get negative value. So the derivative changes from increasing to decreasing. We do get as expected maximum for x equals to square root of 8. Perfect.
Yeah.
So you can now substitute the value and find the maximum area also, which you get 4 in this particular case, right?
Yeah.
Now,
Okay.
tell me, a general expression for what is, if I say that the hypotenuse is, let's say, C, what will be the maximum area? Tell me.
So if hypotenuse is C.
Not 4, C. Then what is going to be the maximum area? So replace 4 with C, then what happens? So when you redo, figure out a general formula also. Is that okay?
Oh, so just
Find a general.
half x square root C squared minus x squared.
Yeah. So this, yeah, it's kind of tricky. With 4, it cancels and gives you that result. So find a general expression, okay? Now, here is the general expression also. So what you should get is this as your general expression. 1/4 of C squared. That's
Oh,
good.
you're supposed to simplify.
Yes.
All right.
It's good to remember this. You know why? If you have a triangle and you want to maximize the area, a right angle triangle, it is always the isosceles triangle. Is that okay? So these two sides, x and y, are equal. Now, that means if my hypotenuse is, let's say, 10, then those two sides are 10 divided by square root 2, 10 divided by square root 2. And the area will be 10 divided by square root 2 times 10 divided by square root 2 times half. And you get your result, 1/4 of hypotenuse square.
Oh.
Easy, right? So you already
Yeah.
have an answer here in this. So while you're working, try to look into general solutions and keep on writing as you move along in your notes. This could be the answer.
Oh. Okay.
So general formula for the area will be kind of like this, and the maximum area will be exactly what I've written there. Clear?
Oh, because maybe later on they'll be like, so what's the general formula? And if I already had it and I wrote it down and said this could be an answer, then I won't time waste again.
Yeah. In your test paper, they'll not give you 4. They'll give you some other value, 5, 10, 50, 100. Who knows, right?
Yeah.
You don't have to care. You know what is this, right? That's the beauty, okay? Now, let's share the solution of question number 2. So you have already done this. Can you read the question and explain me your solution?
Yeah. So consider a cylinder of radius r with fixed capacity of 1,000 centimeter cubed. C. Show that the surface.
Yeah. See, okay. Yeah.
All right. Show that the surface area of the cylinder is A equals 2 pi r squared plus 2,000 over r. And D, show that the rate of change of area with respect to the radius is 0 when r cubed equals 500 over pi.
Correct. How did you do it?
So I also did, so because it's centimeter cubed, I made V equals 1,000 centimeter cubed.
Yes.
Then volume of a cylinder is the circle times the height. So pi r squared h equals 1,000 centimeter cubed.
Correct.
So then I found h simply doing 1,000 over pi r squared.
Correct.
Then surface area of a cylinder is just another formula you need to know. I did 2 pi r squared plus 2 pi r h.
Yes.
Then because we just found h, I subbed that into the formula for surface area. So I got 2 pi r squared plus 2 pi r, then 1,000 over pi r squared.
Perfect.
Then the pi at the bottom of so the 2 pi, that pi there, and then the pi at the bottom, they cancel out.
Yes.
And then the 2 pi r, so that r with the r squared cancels out, leaving r at the bottom. So now we've got 2 times 1,000, which is 2,000 over R.
You're right. So what you did is perfectly fine. And what I did was provided a general solution in this case, right?
All right.
So think like this. If this was not 1,000, but just value V, in that case, as you said, we'll say V equals to pi R square H. So isolate H, V over pi R square. And we know now that the area is 2 pi R square plus 2 pi R H. Instead of H, substitute this value, correct? And once you have this value, you have a general form. Now, in our case, since V, the volume, is 1,000, I substituted 1,000 there, and I got the expression which was required, right? But you don't have to do the general solution. I did it for the benefit of my students so that they understand that in general, the only change which will come is this, twice the volume. That 2,000 is twice the volume. That's what I'm trying to show here, right? Is that clear?
That's
And
really cool to do.
yes, yes.
Yeah.
So the idea is whenever you're working in rate of change and all these application questions, work with general values. You have time now and come out with your own formulas. Check your result with your formula and see whether it works.
Mm.
That
Yes.
should be an added exercise to whatever you're doing, and that should really help you a lot.
Mm.
So that's how you should prepare for a test, right? And that to a big one like GCSE, right?
Mm-hmm. Yeah.
So now you have the area, now easy stuff, find the derivative with respect to R. So it is independent variable R which is changing in this particular case. So we have to differentiate with respect to R. Once we do that, then we get an expression, we can find the critical number, right? And once
Mm-hmm.
you have the critical number, in this particular case, they're only saying, show that the rate of change of area with respect to radius is zero. Zero means a critical number, stationary point. At this particular thing, equate the numerator to zero and get your answer, right?
Mm-hmm.
Perfect. So that was cool. No problems at all, right? Great.
Yeah.
Let's look into the solution of question number 3, Amy. Can you read the question and explain your solution?
Question 3. Consider a sector with area of 100 centimeters squared. D. Find domain of the radius R of the sector. E. Relate perimeter P with radius. And F. Find the minimum value of the perimeter.
Correct.
Right. So with D, so first I started with sector area equals 100 centimeters squared. So you told me not to do it in degrees because calculus is in radians.
Yes.
So you simply write half r squared theta equals 100.
Correct.
And that means theta equals 200 over r squared.
Correct. That's the formula, right?
Yeah. Then I did. Yeah. Oh, okay. So then theta should be less than 2 pi.
Why?
So 2 pi meaning
Full circle.
360. Yeah, because I'm doing it in like
Full
degrees.
circle. You're right.
Yeah, so full circle. So it has to be less than, it obviously can't be more than the full circle because we're in the sector. So that means because theta, it has to be less than the full circle, which is 2 pi. We just found what theta was.
Yeah.
So just sub that back in and you get 200 over r squared being less than 2 pi.
Correct.
So, and then you can, when I cross multiplied, so I got r squared being less than 200 over 2 pi, and cancelling the 2, I got r being
Greater than.
greater than. Did I say it wrong last time?
Earlier, yeah.
Yeah, I did. I just realized, sorry.
Yeah.
I mean, r being greater than square root 100 over pi.
That's perfect. That's perfect. So here the critical point is right there to find the domain of R. Sometimes students really gets, puzzled. What happens, right? They have an
Yeah.
expression, everything is there. So that's a very important part of this particular question, right? We need to find the domain of R, and that's relevant. Again, if I will combine this with the next unit, which is absolute maximum minimum, in that case, we have a boundary condition that are, this could be like from 0 to 2 pi, correct?
Yeah.
So if I put those values, we could get some values which are not valid. And that can help us find the solution without analyzing the first derivative,
Yeah.
right? So we'll actually look into this aspect that many questions could be solved with boundary conditions in lesser number of steps. Clear? So
Right.
let's move on with perimeter now. Yes.
Right. So with the perimeter, what I did was, so we've got the arc length, so it's going to be R plus the like arc
R
length
theta. R theta.
side. Yeah. S. And to find arc length, so I'm just going to quickly show you my conversion. So I know it in degrees, so that's theta over 360 times 2 pi r. But then 2 pi is also 360
Yes,
degrees, so you just cancel it out. So to get it into radians, it will just be theta r.
you're right. Theta is correct. Yes.
So that means side equals theta r.
Yes.
So we just found theta, didn't we? Yeah.
Correct. We did.
So I did r times 200 over r squared, which was theta,
Yes.
equals 200 r over r squared. And the r's cancel, leaving an r at the bottom. So we get 200 over r.
Yes.
So that means the perimeter would be 2r, because it's r plus r, the 2 radians, and then the arc length, which we just found, which is 200 over r.
Perfect. Perfect.
Yeah. Okay.
That's correct. And then the minimum value of P.
Yeah. So minimum value. The moment you hear that, you should know first derivative. So we just found what P was. So the derivative of that, so 2r derivative would just be 2. And 200 over r derivative would be minus 200 over r squared.
Correct.
So I made 2 minus 200 over r squared equals 0.
Yes. Yeah.
And then I did 2 equals, I brought the 200 to the right hand side. So 2 equals 200 over r squared. 2r squared equals 200, just cross multiplied. R squared equals 100. R equals 10.
Perfect.
Is that what you
R equals to 10 is your critical number, stationary point. Correct.
Yeah.
Then how did you analyze?
So then we used our favorite interval table.
Yes.
Chose 2 test points, so 9 and 11. Put those test points into the derivative.
Yes.
And I got 9 being negative and 11 being positive. So because it goes from decreasing to increasing, we got a minimum at r equals to 10.
Perfect.
So what I did was I just subbed the r into the perimeter, which we found in E. So P equals 2r plus 200 over r.
Yes.
Then P equals 2 times 10, which is 20. Add 200 over 10, which is 20. So 20 at 20 is 40 centimeters.
Good job. Very good job. Excellent. So Amy, I'll request you to again perform all these calculations taking area as A, not 100. Okay. So when you take area as capital A, for example, you'll come out with general result. And put that on the side so that you always remember these types of questions should give you that kind of result. Is that clear to you?
Yeah.
So I hope that was a good exercise, and I really appreciate that within such a short time we could provide solutions and share them with us, right? That's great. How do you find today's exercise, Amy?
Really helpful. Yeah, like just from beginning of that whole general solution thing. I never used to do that, but now I'm thinking about it. There has been so many questions where I go through it, and because I don't do the general solution thing, I've got like values there. They would ask the next one, what happened if n was 500? And I
Yes.
have to do the whole thing again. But if I just started with a general solution, I could just sub that value back in and
Correct.
done, move on.
Yes.
Then there were other things where there are shortcuts, and obviously always try and find the quickest route to doing so. With the whole arc length and sector, I was doing it in degrees, but make sure you convert it to radians. That's
Yeah.
not that hard though, because once you know, if you know one of them, you're okay. Just make sure it's radians. And yeah, I think that was all really helpful. Just knowing the first derivative and all the points and everything. That was really good.
Now, at this stage, let me give you a heads up about what we are getting into soon. In calculus, most of the questions which you're going to get will be based on different kinds of shapes. For example, you'll begin with lines, parabola, cubic functions, right? Those are different curves. And then, as far as 3D shapes are concerned, we may have a sphere, we have a cone, right? We may have a prism, a kind of pyramid, different kinds of shapes, right? Then
Yeah.
we'll also come across the examples where we have one geometrical shape inside the other, and we want to maximize or minimize area or things like that. So that is to say, the question could be, what could be the maximum area of a rectangle inscribed in a hemisphere? I mean, I should say a circle, a semicircle, right? So that those kinds of questions. Now,
Right.
we have already seen today examples like sectors and all. What I'm trying to say here is that you should also categorize your examples into shapes so that once you have, let's say, prism, right? You should look into prism and see all related questions on prism. Like, where did we go, right? What was the formula? What did we do? And how did we do, correct?
Oh, okay.
So, like, you have examples where we have a trough, and in that you can make a prism, and then you're pouring water into this. That could be a huge question. And once you put them all together, you have a very good understanding of how to do those kinds of questions.
Yeah, that's
So,
good.
yeah. Similarly, for trigonometry, like the sector thing we did, and you're struggling with the radian part, I like you to
Yeah.
on that and do some practice questions on radians. Think in terms of radians, not in degrees. Don't convert.
Okay.
Think in terms of radians, and that is my advice to you at this stage, especially for calculus. Okay,
Okay.
don't think in terms of degrees. Straight
Okay.
radians, right? So
Yeah.
that should help. But overall, it was fantastic. I'm very happy about the way you are learning. And I think next topic I should take up with you is the boundary conditions, the absolute maximum, absolute minimum. And then we'll take up more application questions with different kinds of shapes. Okay?
Okay. Cool. Thank you so much, sir.
Thanks. Thank you. Bye.
Have a good rest of your day.
You too. Thanks.
Thanks.